In this lecture, we're going to study using the effect of initial stress on a membrane, like a drum head which is tuned for a certain pitch. So basically, by applying initial stress through tuning, we can determine the pitch or the natural frequency of a membrane. We're going to use a 7-inch radius drum head or membrane with material properties of nylon as a material used for drum heads. The equation for natural frequencies of such a drum head is given in this equation. The natural frequencies are given by these values. Beta is the zeros of first kind Bessel function, which is J. Sigma is the initial stress or pre-stress applied to the membrane. Then we have R, which is the radius of the membrane, and rho is the density. And if you use these values for 100 megapascal initial stress applied to this drum with this radius 7, these are the natural frequencies that we're expecting to receive from the ANSYS model. So let's try this in ANSYS APDL. First thing I want to do is to change the file name, because I'm going to need to do two solutions, one static for applying the initial stress and then modal analysis in the second to get the natural frequencies and mode shapes. So in order to make sure that ANSYS knows where to read the initial stresses, I changed the file name to a name that is different from default file. I call it membrane. And then I want to give some parameters. Conversion ratio. I want to call it 25 E minus, or 25.4 E minus 3. And the radius is 7 inches times the conversion ratio. It didn't, oh, I have to call it conversion ratio. Now starting prep 7 or pre-processing and picking the element type 281, which is a shell element, and I have to give a reference number, which is a higher order shell element. And I need to ensure that this is a membrane and not a shell, so I want to remove the bending moments. So I say key option. For the first element type, key option 1 and value is 1. And the way to remember these is to reading the help documentation for the element type. So if I come here in element type, add edit 281, if I click options, the first key option determines the stiffness of the element. The first one by default is bending and membrane. The value for this is 0. Key option 1, if set to 1, only uses the membrane values. So by doing 1 there, I enabled the membrane only stiffness. Now I have to define material properties. So I say MP EX for Young's modulus, first material model. And the value is 4.9 E9, 4.9 gigapascals. And then the Poisson ratio for the first material model is 0.3. And the density for the first material model is 1390, the value that I want to give. Now I have to define the thickness of the shell or the membrane. So I use sect for section type. First one is a shell. And the data is thickness. I want to use 1 millimeter. Material model 1. Orientation is 0, which doesn't really matter in here because it's isotropic material. And let's use 5 integration points. Now I want to define key points. First key point I want to define is at the center. So pick 0, 0. And then I want to define a key point at x equals radius and y equals 0. So it's made in there. And then I want to create another key point at x0 and y is radius. So the 3 key points are made. I need to use these key points to create lines. First line is between key points 1 and 2. Then key points 1 and 3. And then an arc between key points 2 and 3 with the center at 1, and the radius is given by that rad parameter that I defined. So LARC, bending key points 2 and 3, center is 1, and radius is rad. I want to use these lines to create an area, so I do AL. I can use 1, 2, 3, or I could also say AL comma all. I could do this, and now I need to mesh it. The first thing I want to do is to determine the element size. I want to make sure that they are at least 20th or at most 20th of a radius. So I say E size comma rad over 20, and activate the element type 1, material model 1, and section number 1, and do a mesh 1 because I only have one area. So the mesh is created, and I actually want to make a full model here. So I do AR sim and X direction, which means YZ plane, all the areas. If I do E plot, now what I have to do is to merge the nodes at X equals 0 because I have nodes falling on top of each other here, or coincident nodes. So I say N cell S for selection, look for location, X for the direction, and value 0, and do num merge all, and all cell. Now I want to do the same thing. I say AR sim and Y direction, all the areas. Again, if I do E plot, now I have to select the nodes at Y equals 0. So I can say N cell S by location Y 0, and num merge all cell. Now what I want to do is to make sure that the perimeter of this circle or membrane is fixed in all direction. So first thing I want to do is to change the coordinate system to cylindrical, and then say N cell S location X, which in this case is going to be the radius, and the value is actually the rad parameter that I defined earlier. So if I do N plot, I can see all the nodes are selected, and the radius or the perimeter of the circle, I can say D all comma 0. So all the degrees of freedom are 0. I want to do all cell and E plot. And before I move on, I want to change the coordinate system back to Cartesian. So the model is ready for solution. Like I said before, I need to do two solutions here. One is to apply the initial stress, and the other one is to apply the modal analysis. So I start solution, and I say, so I have to start solution, and I say N type static for the stage at which I'm going to apply the initial stress. And in order to apply the initial stress, I have to use any state command, which is not available in the menu. So let's just see how it works by looking at it in the help documentation. So if I come here, find the command window and command references, find I, and find the any state, which is here. There are several actions I can take. One of them is set, and the other one is define, the two main ones that I want to use. The set is basically determining what data type I want to use. So by default it's stress, but I want to use the command to make sure that I am applying initial stress. And the way I want to select the elements, I want to pick them by material ID, and basically I have material ID 1 that I want to pick there. And then next I have to define. So the next action is to define the values. So I can come here in the define section, which element IDs, which I have to use all, and then the layers and the parameter input that I can give, stresses and strains and everything else that I can apply in CXX, CYY, and CZZ here. So I start in a state by giving set and then D type, which is data type, stress. So I want to apply initial stress. And in a state, set material 1, so I only apply everything to material model 1. Now let's define the values for all, and I apply 3 commas there. And the stress that I want to apply is 100 megapascals. So if I give 1E8, it would apply 100 megapascal stress in all directions. Now what I have to do is just to solve this analysis. So I do solve, and the solution is done. And close this window, say finish, and start another solution. Now this time I want to apply modal. So I do ntype, comma modal, and first I want to determine the options. So MOD, modal options. I want to use the block Langsos method to define the mode shapes. So I say lamp for that. A number of nodes 7, and I don't want to give any initial or ending stresses, or frequencies for natural frequencies, and I want to turn on the complex computations. Then I want to say mexpand, expanding the modal analysis. I still want to get 7 nodes or 7 modes, and I want to do element calculations, and I want to set pre-stress on. So if I do pre-stress on, let's find that in the documentation first. Pre-stress is a command that I should be able to find pretty soon here. Specify whether pre-stress effects are calculated or included. So if I do that, I say press on and solve this, I will see that the solution is completed, and I can do finish and start post-processing and do set comma list to see the natural frequencies of this membrane, that if I compare with the natural frequencies of my ANSYS model or coding, let me zoom in here so I can see them better. They match pretty well. The first one, and I have 7 natural frequencies, but as you can see, some of them are duplicate. So the second and third are the same, fourth and fifth also the same. And let me show you why that's happening. Let me maximize ANSYS and find the natural frequencies. So if I do set comma 1 comma 1 and do pln sol u z, and let's see if I can rotate it. So for this one, the mode shape is like that. The center point is moving up and down, and the sides are basically fixed. But if I do set next to get the second mode shape and do pln sol u z again, you can see that we have 2 points which move up and down. And if I do set next again and do pln sol, you see that the locations of these points are shifted by 90 degrees. So that's why we have 2 natural frequencies of the same value, but basically they're the same, the mode shapes are the same. The only thing is that it's shifted by 90 degrees, which for a circle, it's basically the same, and we can ignore the duplicate natural frequencies. The same is happening to the next natural frequencies. So I have 4 points of peaks and valleys, which again, if I do next, I'll see that they are shifted by 90 degrees, just like that. So I can ignore that duplicate. And then I can look at the natural frequency of the 7th natural frequency. So if I say set next, pln sol u z. So I can find out that this is the 6th natural frequency. So we ran this analysis. We applied initial stress to a membrane and found the natural frequencies of a membrane which resembles a drumhead